Thanks everybody for being here. I'm Raffaele de Biasi, and alongside the people we work together, today I'm going to talk about tensile testing of lattice structure. So this is a work conducted in collaboration with the University of Trento, University of Rome, and University of Pisa. So let's start about talking. We talk a lot during these days about lattice structures, and many of the possible configuration of testing that we have seen in these days are actually under compressive loads. This is very straightforward when dealing with lattice structures because you simply can take your component, then you have two plates, and then you crash basically your component between the two plates. This is not as easy if you want to apply tensile loading, of course, because you can imagine it's challenging to connect your porous component to the machine. Therefore, there are some examples of philosophy you can have dealing with tensile specimen. So the first one I'm going to show is the dog bone specimen. So this resembles quite closely a dog bone for classical materials, but instead we have here a metamaterial, so something which is porous. This has very clear advantages. So it clearly delivers the tensile loading inside the metamaterial, but also is in contrast with one of the main driving philosophy from the ISO standard, the only that is available for lattice structure, which is the 13314, which considers the need of having at least 10 repetition of the unit cell inside your specimen. So this is more about testing a structure, maybe with respect to testing a metamaterial itself. So we need to increase the number of cells along the cross-section, and there are two other ways in which you can do that. The first one is extremely smart, in my opinion, because you take your component, as you will be for compressive test, and you bond it, basically, at the extrema. It has, of course, some problems, because if you need to bond each and every component to your machine, to your uniaxial testing machine, well, it's of course challenging from a, let's say, practical point of view. So let's move to the last configuration, which is exploiting a component having three main parts. The central part is a gauge part, so the porous material that you really want to test. And then you have two different extrema at the top of the bottom, which are solid, so you can easily grab to your tensile machine. And then, of course, there is a region which stays in between, which is a transition region that is able to connect these two. Okay, so what are then, if you want to design a tensile specimen, what are the requirements for that? Well, we consider three, and of course the first one is the easiest. So you need to deliver the load from the machine to your specimen. But of course, you also want to have an isocritical region inside your gauge part. Otherwise, you will not be testing the entire material, but only a part of it. And in the last one is that we need to ensure the failure inside this specific region and not, for instance, at the connection with the machine. So we propose the following geometry, which is, of course, is following the third philosophy that we have seen before, and is composed by a gauge region in the center, providing 8 cells in axial and also lateral direction. And then we have a base, which we are going to connect to the uniaxial testing machine. And then we have a transition region, which is composed by different cells. And the idea here is to optimize both the transition region and the specimen base in order to achieve this requirement that we have here. Okay, how to do that? Well, we employed a two-step optimization problem. So we have, firstly, optimization of the material distribution inside the transition region. So basically, we want to exploit the potentiality of additive manufacturing in order to deliver the material where it's needed and to remove it where it's not, of course, in order to provide a suitable stress distribution along the gauge the gauge part. And with the same aim, we also are gonna apply optimization problem to the base geometry. So we of course need to provide some metrics, so some index, in order to understand if our design is good or not. And to do so, we need to face first a computational challenge, because if I need to design a component which is so complex, which is containing many lattice structure cells, we need, of course, to solve an important computational problem. To do so, well, we started this project some years ago, and we tried with solid elements. We failed because we found, of course, an high accuracy for the result of this modeling technique, but it's also extremely computationally demanding, and also we found some results which were mesh dependent, which is not great. So we took a step back and developed a computationally efficient modeling technique, which is based on beam elements. So this one is basically starting on the idea that if you have strut-based lattice structures, well, these components are mainly one-dimensional elements, so why not simulating them with beam elements? That's okay. But if you do it like straightforward, you consider nodal location, which is oversimplified. So if you consider here your solid model, the nodal location is a finite volume. But if you consider it only with beam elements, the struts are connecting in a zero-dimensional node, which is not representative of this real geometry. So how to fix this? Well, we developed a compensation method able to provide an increment for a given length of the strut diameter. This is taking care of the mismatch in the stiffness of the components, so for the different simulation techniques. So we can provide different charts for different cell topology based on different, let's say, porosity. This is basically porosity, and here we have the compensation coefficient. So once we have this tool, we can go back and try to solve the problem that we were discussing before. So the overall model is composed by compensated beam elements in the lattice region, and then we have a solid part for the base material, of course, for the base of the lattice specimen. Of course, we took also advantage of the symmetry of this component in order to reduce the computational cost. And we lack also of something that is telling us how critical is our component and how the stress are distributed. So now we took advantage of the average strain energy density to do so. This is, let's say, an improper use of this method, but it helps us to understand where are the most critical locations inside our lattice structures. So thanks to the people who presented days before me, you know quite well what is average strain energy density, but in principle, this is an energetic method able to understand when the stresses, or let's say the energy better, inside a specific critical location is high enough in order to open a crack. We are not going to use this matrix, so this index for this aim, but instead we are going to define some critical cross-section that we want to consider inside our component, and for each and every nodal location of this, we're going to average the strain energy density inside the nodal location. And we also take the square root of this value in order to be proportional with stresses, because you remember, of course, that is proportional to the square root, the power of 2. So given that, we can definitely now state the optimization problems. So we have a two-step optimization problem. The first one deals with the definition of how this transition region should be designed. And to do so, we take the average strain energy density distribution inside these two sections here, and we want them to be as low as possible. So we really want the difference among the maximum and the minimum to be as little as possible. And then we can also take care of some other constraints that are considering the manufacturability of this component. So we can set a boundary on the dimension of the struts. Plus, we have this last one, which is setting that the section number 3 should be less critical with respect to the other two. Otherwise, we promote the failure in this region here. The same can be done, basically consider the base geometry and acting on these design parameters that we have here. So let me present you the result of this study. Before, I didn't mention how many layers we have in the transition region, because we conducted a parametric study in order to understand how big this transition region should be. And you can see you can start with only one layer, so one cell in the transition region, reaching up to 5. You easily understand that if you want to test something, you want to reduce as much as possible the unnecessary material. So the lower number of transition cell, let's say, the better. But we found out that actually the lowest, there is no asymptote in this, and maybe it's coming after this, but we select only the lowest possible average strain energy density variation, which is linked to 5 cells in the transition region. We didn't want to go above that, otherwise it starts to become economically very difficult to sustain. Okay, so this is how this transition region should be designed, considering a specific case for a specific case study for the lattice structure inside this. So we selected one specific cell, which is the BCC cell, but with the proposed methodology, you can easily address whatever strut topology you like. So this we selected this equation in order to change both in the axial and radial direction the distribution of the strut dimension. And these are the charts that are linking the different cell dimension and the porosity basically to the different coefficients of this equation. So the same can be done also for the base optimization, where you have these parameters that are normalized over the cell dimension in order to seek generality. And once we have done this, of course, we can take also a look on the stress distribution. So this is the average strain energy density distribution over the cross-section. And if we look at the Fumisa stresses, for instance, here, you can notice that here we have very low stresses nearby the transition between the solid material and the porous one, while we have an increment of the critical stresses nearby the gauge location, and you can also visually inspect the fact that they're almost the same. So we reach also an isocritical stress in this location. Now it comes into play the validation, and to do that, we printed some specimen in using this BCC cell. We take advantage of the polymeric printing materials, and basically this is PA12 with MJF technology. And I would like to thank my colleague from University of Pisa to take these measurements because they also use the DIC equipment in order to compare what are the actual deformation that we measured during the testing of the specimen with respect to the simulation that we conducted. So these are the displacement that we have in the experimental component and the, let's say, digital twin of it. So we can also consider the how can I say, stress versus strain. And of course, the simulation that we considered was a linear elastic one. So if we consider only some points on this, we can enter in this chart and see if there is a difference between our simulation and the experimental points. We find that there is not as soon as we are in the elastic region, but if we go, of course, into the plastic region, the models falls apart because it's not considering this part of the behavior. And also, we tested specimen, and all of them failed in the central part, which is great. So we don't have failure nearby the junction between the solid material, and the porous one. Okay, so these are my results. So we were able to develop a geometry in order to fulfill the design requirement that we state. We also developed a two-step optimization problem, as I described. We found a computationally efficient tool for obtaining lattice structure simulation. We determined the geometrical parameters for a given case study, and we also were able to validate that experimentally. So let me acknowledge the findings that made this available, which were on the Butterfly project by Professor Berto. And this is it from my side, and I'm open for discussion. Thank you very much.